Blaise Pascal, who did a lot of work on fluids and for whom we've named the unit of pressure, um, did his work in sort of the mid of the 1600s. He lived about 40 years, so 1620 to 1660, somewhere in that range. Um, and one of his principles that if you have an incompressible fluid, right, incompressible like canola oil or for the most part water, but mostly we use oils when we talk about incompressible because water is ever so tiny bit compressible. Um, if you have an incompressible fluid, then the pressure in it is the same everywhere. I mean, that's the essence of Pascal's principle, that because you cannot compress the fluid, the pressure in it is the same everywhere. Now, some of you may say, but we just talked about pressure varying with depth in a fluid. Yes, and let's just say, other than the change in depth, but you'll see here we've got two pistons pressing down on the fluid at the same height. And so, yeah, height makes a difference. But other than the depth that you're at in the fluid, the pressure in a fluid is the same everywhere. What are the consequences of this, right? Well, what does this mean for pressure is just force divided by area. So if the pressure here and the pressure here are the same, then F1 divided by A1 equals F2 divided by A2. Well, that has consequences. And we actually use this all the time in making brakes, right? For instance, if you have standard disc brakes, you have a master cylinder that's small that you push a good distance, and so you're going to make this cylinder. You're going to make this cylinder move quite a bit, and then the cylinder at the brakes is going to move a little bit. And what you're talking about is the difference in size, and so that you get the force you need here versus the force you need there, and you get the amount of motion you need here versus the amount of motion you need there, and the overall work you do is the same, but the distance you move is different. So if you look through this example um, of the work done, which is just force times distance, right? The work done as you move one piston versus the work done as the other is moved. The work is the same on both sides. Energy conservation holds, but the amount of motion, right, is smaller. Basically, when you move the small piston, you're squeezing a volume here over into a volume here. But because the volume on this side is so much broader, the area on this side is so much broader, the 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 depth that it has to move is less. Right? And so this kind of gets us into the essence of Pascal's principle and how it plays out as we um, as we go through this. And the key again is in a incompressible fluid, the pressure at any given level is the same everywhere in the fluid. And so it doesn't matter how many different times it comes up. It'll all be at any given air level. You can go across here, you can go across here. The pressure is the same.